Hey guys, welcome Kaitlin from MongoDB.
Hi, everyone. Thanks for coming today. Let's just dive right into it and start by talking about what encoding and decoding actually are. So encoding is the process of taking a Swift type, which could be something very basic like an int, or it could be some instance of a complex class. We put it into an encoder, and we get out data in some external representation. And that could be JSON or XML, or really any format that you can construct programmatically. Throughout this talk, when I talk about encoding, I want you to think of putting values into a box. And so when I talk about encoding, I'll show you this little inbox icon. Decoding is basically the reverse of that process. So we start off with the external representation, which could be JSON or XML or anything that you could parse programmatically. And what we get out is an instance of a Swift type. So throughout this talk, when I talk about decoding, I want you to think about taking Swift types out of a box. Why would you want to do this? The short answer is that encoding and decoding allow you to transfer data in and out of your application. So for example, maybe you're communicating with a REST API that understands JSON, and you need to be able to send your Swift data types to it. Encoding will allow you to do that. Or maybe you are reading from and writing to a database, and you want to be able to translate your Swift types into the format the database understands. That's actually how I've gotten sort of very deep into encoding and decoding, writing the MongoDB Swift driver, since we allow you to put your Swift types into the database and pull them out. Or maybe you're just reading data to and from files that are in JSON or some other format. In all these cases, encoding and decoding are going to allow you to transfer that information. Swift 4 introduced a standardized approach to doing encoding and decoding, and today we're going to talk all about how that actually works, starting off with sort of the most basic use cases, building up to more complex ones. So starting with the basics. One of the main building blocks of the sort of whole codable system is the Encodable Protocol, and it just has this single method in code that encodes the value to the provided encoder. So that's basically the only job of an encodable type, to know how to write itself into that encoder. And a lot of types have built-in support for encodable. So numbers, Booleans, strings, all conform. And then for all these types that sort of contain other types, like an array or a set or a dictionary or an optional, those all conform if the types that they contain conform to encodable. And then a bunch of the foundation types come with built-in support for encodable as well. And some other things to note about this are that if you are not using one of those types, well, let me step back. If you are not using one of those types, but if all the properties that your type stores are encodable, so maybe your property or your struct is composed of like entirely strings, then you'll get conformance for free. But if that's not the case, or if you don't want the sort of default conformance that the compiler provides you, then you can provide a custom implementation of this method, which we'll talk a little bit more about later. And one other thing I want to call out about this method is that it's format agnostic. So you'll notice this method doesn't actually specify anything about the type of encoder I'm using, just that it is an encoder. So you only need to conform to this protocol one time, and then your type can be used with any encoder, which is pretty awesome. On the flip side of encodable is the decodable protocol. So this protocol has a single method, which is an initializer, that takes in a decoder and initializes an instance of the type by reading data out of the decoder. And much like encodable, all these same types come with built-in support for decodable. And it's kind of the same story as encodable here. So you'll get automatic conformance if all the properties your type stores are decodable. But you can provide a custom implementation if not. And just like the encodable protocol, this protocol doesn't actually care about the format that you are decoding from. So that's pretty cool. So it's pretty common you want to be able to go both ways with your data types, both encode and decode them. So the standard library actually contains this type alias codable, which means encodable and decodable. So how do you actually make a type codable? Let's start off with a simple example of a cat, which stores two properties, a name and a color, which are both strings. If I want to make this type codable, all I really need to do is edit the declaration to make it codable. And that's it. Now it's codable. So how would we actually use this type with an encoder or decoder? Let's start off by creating an instance of cat for my cat, Roscoe, and use him with an encoder. So I'm going to use Json Encoder as an example here because it's probably the most commonly used one. It's part of the standard library. So this encoder has a pretty simple API. It has one method, and that method takes in an encodable value of some encodable type. And what you get out is UTF-8 encoded data. UTF-8 is just sort of a format for encoding characters. It's like how Swift strings store their data under the hood. So if I wanted to use Roscoe with this encoder, I'm going to start off by creating an instance of the encoder. And then I'm going to pass Roscoe into the encoder. And I get out some data. Now, this data is UTF-8 encoded, as I mentioned before. So if I were to print it out, it would just be a bunch of numbers. It wouldn't make much sense to most of us. So I'm going to take the extra step of creating a string using that UTF-8 encoded data. And this is going to allow us to see what the JSON actually looks like. And now if we print that out, you see we've got this nice JSON object that matches the cat that we started out with. So what if we wanted to use Roscoe with a decoder? So the JSON decoder provides a pretty symmetric API to JSON encoder. In this case, we need to pass in the type that we want to decode to, as well as the data we're decoding from. And what we get out is the value of that type that we requested. And we need to specify a type, since just based on the JSON, the decoder has no idea what type we wanted to get out. So using this decoder, we'll create an instance of JSON decoder. And then we're going to pass in the cat type that we want out, as well as the data we got from encoding, since we know that's like properly UTF-8 encoded data. And then we can print out the resulting struct. And we see we start off with, or we get back this struct that just matches the one that we started off with. So we've sort of successfully round-tripped this cat through JSON now. So that's basically it for basic usage of these protocols. But now let's kind of move on to the more advanced stuff. So in this case, so far we've just been going along with the automatic conformance. But maybe we want to do something sort of special when we're encoding or decoding. For example, maybe we want to rename a key. So right now, if I encode this cat, I'm going to get out this data where I have these two keys, name and color, corresponding to properties. But maybe I'm talking to some API that expects me to send the name as first name. Maybe there's some optional last name field I'm not sending or something like that. How could I do that? So the answer is something called coding keys. So coding keys is a special nested type that specifies the keys a type will use when it's encoded or decoded. And by default, the compiler is usually generating these for you. But you can provide a custom implementation if you want. So these ones I'm showing right here is what it would generate by default, where there's one case corresponding to each property that your type has. So if we wanted to provide a custom implementation of this to rename a key, we can do something pretty cool, which is we give a raw type of our enum. We give the raw type of our enum as a string. And then we're able to override the string value for a particular case. So in this case, I'm saying encode the name property under the string first name, and just encode color under the string color. And so if I do that, and then I encode my cat, I will get this output that I want, where the key is renamed. So you can also use coding keys to do something like omit a key. So for example, if I just left out the color case in the enum, the color wouldn't get encoded at all. OK. So we kind of talked about doing stuff with the keys now. But what if you want to modify the things that you're encoding as you encode them? So maybe I'm talking to an API that's case sensitive, right? And I have to send the cat's name in lowercase. But I'd like to keep it with the correct capitalization within my Swift application. So if we want to do this kind of customization, we need to dig a little deeper and come back to the encode method on the Encodable Protocol. And we can actually provide a custom implementation of this to accomplish what we want. But in order to do that, I want to talk a little bit first about what the Encoder Protocol actually looks like, because that's what we need to use to do this customizing. So basically, the main job of an encoder is to provide containers, which are views into its internal storage. And you can put values into these containers to sort of construct the right structure that you want to get output. There are three types of values you can put into a container. The three types of containers you can get from an encoder. And the first is a single value container, which is meant for encoding at some type that can be represented by just a single value, like maybe a string. The next is an unkeyed container, which is meant for encoding a sequence of values. So it's sort of like an array. And the last is a keyed container, which is meant for encoding key-value pairs, kind of like a dictionary. And each of these containers will allow you to put 3 different types of values into them. So I like to think of these as 2 base cases and 1 recursive case. And the first base case is nil, which might have a different meaning depending on the particular output format that your encoder produces. In the case of JSON, this is like JSON or JavaScript null. The second base case is a primitive value. So that's like a Swift type that you can't further break down into other types, like a Boolean or a string or anything like that. And the third case is the recursive case, which is when you actually want to put some encodable type in that's composed of other encodable types. And we'll talk a little bit more about how you use that third case in a little bit. But how do you actually use these containers? So let's revisit our cat example. In this case, we want to encode this name and color to the encoder. And so we have these 2 name properties, so it seems like it's probably a good fit for a keyed encoding container, where the keys would be name and color. And under name, we'd want to put Roscoe in, and under color, we'd want to put orange. So that's how cat sort of gets translated into containers in this case. And how does the encode method for this actually look? Like, how do we build those containers using code? Well, first, we're going to need coding keys, like we saw before, with a case corresponding to each property. And then we're going to need this encode method. And so that takes in the encoder. And the first thing we're going to do is ask the encoder for a keyed container. And we're going to tell it what kind of keys we're using, which is this coding key struct, or ename that we passed in. And then now we've got a container set up where the only keys we're allowed to store values under are name and color. And then we're going to fill in the name property for the key name, and then fill in the color for the key color. And that's how we sort of construct these containers. So if this is how you want your output to look, you should not write any of this code. This is what the compiler would be generating for you. But now that you know what the compiler would do, you can probably imagine how we might modify this code a little bit to get some sort of different output. So returning to our example of converting a string to lowercase, what we would do in that case is sort of revisit that code I just showed you. But instead of passing in just the name for the name property, we could pass in name.lowercase and get this result that we want. So this is a pretty simple customization, but you can imagine you could do all sorts of interesting transformations of your data, or call some API, or look something up in a database in order to decide what exactly gets encoded for your properties here. So now I want to talk about making things a little more complicated, where you have types nested within other types. So far, we've just been talking about this sort of flat struct that has 2 properties. So let's make it a little more complicated and introduce a cat owner struct. So a cat owner stores both a name and an array of cats. So as was mentioned in the introduction, I actually have 2 cats. So this is my second cat, Chester. So let's make cats for both Chester and Roscoe and create a cat owner, Kaitlin, who stores those 2 cats. So if we wanted to make cat owner encodable, it would be pretty trivial, because cat conforms to encodable already, as we know. And then cat owner has these 2 properties. The first is a string, which is encodable. And the second is an array, which is composed of a encodable type, cat. So cat owner will also get conformance to encodable for free. And if we were to encode that cat owner we just created with a JSON encoder, we'd get output that looks like this, which is the 2 top-level keys, and then cats is an array of objects. So how does that happen in terms of code and containers? So we start off with the encoder, and then at the top level, we've got these 2 named properties again. So we'd probably want a keyed container. And in the name slot, we'd put Kaitlin. And then in cats, we want to store more than 1 value, right? We actually need to store this sequence of values. But this is just a spot for like 1 value, right? So what we actually want here is a nested container, which encoders support as well. And in this case, we want an unkeyed one, since we've got this sequence of cats to put in. And so in the first spot of the unkeyed container, we want to put a cat. But remember, we saw before that a cat actually needs a keyed container. So now we're going to nest containers again and put a nested keyed container within our unkeyed container. And we'll have one there for the first cat, and then in the second slot, we will put in the second cat. So that's how cat owner sort of gets translated into containers. So how does that actually happen in code behind the scenes? So coming back to our struct definition here, we're going to want some coding keys, right? One for name, one for cats, pretty similar to what we saw with the cat example. And then for the encode method, the first thing we're going to do is request a keyed container that uses those particular keys. And then we're going to put in name for the first slot. And then we're going to put cats in the second slot. So whoa, like 3 boxes appeared at once when I made that one call. So what's going on in that line of code? So actually what's happening there when we make that call is that we're visiting this sort of case I talked about before, the recursive case, where we're putting an encodable type into a container. So when that happens, we actually end up calling the array implementation of the encode method from the Decodable Protocol. So let's visit what that looks like quickly. So for an array, what we want to do is ask the encoder for an unkeyed container, right? Since we've got a sequence to put in. And then we want to iterate over all the values that are contained in the array and encode them to the container. And the encoder is doing something pretty cool here, where it's actually tracking how many values we've encoded so far and sort of what depth level of recursion we're at. So the encoder knows that when the array here requests the unkeyed container, that it should actually be nested in this spot that we were in. And you don't have to do any of the work to sort of specially handle this sort of depth that you're at, which is pretty awesome. So you'll also notice in here that when we call container.encodeElt, we are passing in another encodable type there. And when we do that, we do another sort of level of recursion down to the cat encode method. So then when we request a keyed container here, that gets properly nested at the right spot. We fill that in, and then we do the same for the other cat. So the compiler and the encoder are sort of doing all this for you if you want your output to look just like what I've given here. But now that you understand how sort of containers get nested within each other, you probably see how you might be able to use these to restructure where things get placed and move values to different levels and that sort of thing. So let's talk about one example of how you might do that, flattening data. So maybe instead of sending the whole cat struct to whatever API or database I'm talking to, I just want to send a string in place of each cat. I don't want to send something like just the name. I just want to send a string. So my output would look something like this if I encoded that cat owner. How could I do that? So the trick here is to think about these spots where we put the cat names as single value containers. So sort of any place you put a single value could be a single value container, but you don't always explicitly need to request a single value container. So in this case, to accomplish what we want, I'm actually going to revisit the cat encodable implementation because we want to change how each cat is encoded, not how the cat owner is encoded. So in that case, we're going to write a new encode method here. And the first thing it's going to do is request a single value container, which will hold a single value. And then we're going to put the name into that container. And that's basically it. You'll notice we didn't need to use any coding keys since we are not encoding using any keys. We're just putting one property in. So doing this, plus leaving the cat owner encodable implementation exactly as it is, and just letting the compiler do the work, will give us that output we want where the cats are flattened into strings. So at this point, you might be like, isn't this talk also about decoding? We've only been talking about encoding so far. And that's true. But I'm actually not going to spend much time on decoding at all, because it's kind of the same thing. Before I talked about how encoding is putting values into a box and decoding is taking them out. But that's kind of where the differences stop. So like translating a cat into decoding container land, you'll notice looks exactly the same as the encoding container structure did. And if we were to sort of write out what the compiler would do to make this cat decodable, it would use these coding keys, which are exactly like we saw before. And then we would have this decode method, which would start off by requesting a keyed container using our coding keys, just like what we did before. And then for each property, rather than putting it into the encoder, we would pull it out by decoding a string and passing in the key we want to decode it from. So we're looking in this place that we would have put the value before when we were encoding it. But we're able to decode by doing exactly the same thing. basically. So all the kind of customizations we've talked about so far will also apply to decoding, since you can use the same container structure and all that sort of thing. Again, this is what the compiler generates, so you shouldn't write these if this is sort of how your data should be decoded. But you can tweak these if you want something a little different. So the main takeaways I want you to have from customization are these. First, you can use coding keys to customize which properties get encoded and decoded, and what names they're encoded and decoded from. And then you can use custom implementations of the encodable and decodable protocol methods in order to transform your data and to restructure your data as you're encoding and decoding. OK, now I want to briefly touch on what I would call super advanced usage of this stuff, which is writing your own encoders and decoders. So I got pretty deep into this, writing a Json Encoder and Json Decoder for the MongoDB driver to transform Swift types to and from MongoDB documents. And I think the best way to kind of get started doing this is just looking at prior art, which is already existing encoders and decoders. So I spent a lot of time looking through the Json Encoder, Json Decoder code to do this. And now I'm going to tell you a little bit about how that encoder and decoder work. So one thing you'll notice as soon as you start kind of looking at Json Encoder kind of closely is that its API doesn't match the Encodable Protocol. Json Encoder has a single method where you give a value to the encoder to encode. But the Encodable Protocol has this single method where you give the encoder to the value. So what's going on here? Like, why don't these match? The answer is that something that calls itself an encoder doesn't necessarily conform to the Encoder Protocol. So in fact, Json Encoder is designed where there's this public Json encoder type, and then a private _JSON encoder that actually conforms to the Encoder Protocol. And so the JSON encoder just provides that single method, and the _encoder actually provides the container API. The short answer of why this is done is to sort of separate API concerns so that you see them at the correct levels. I don't really have time to go into it today, but I did write a blog post about this recently. So if you are interested in learning more about sort of why the APIs are designed that way, I recommend checking this out. Beyond the private encoder type, Json Encoder also has this private type called JSON encoding storage. And this is what you are reading from and writing to, or this is what you are writing to when you use this sort of container-based API. And both of these are private. And JSON encoding storage, let's talk a little bit about what's going on inside there. So this is backed by either an NS dictionary or an NS array. It's going to be an NS array if the sort of first container that you request when you're encoding something is unkeyed. And otherwise, it's going to be an NS dictionary for a keyed container. And the container API is what's used to actually sort of construct and put values into this NS dictionary or NS array. And why are we using NS? The answer is that that's what JSON serialization supports using. So under the hood, the encoder is using JSON serialization to convert a type to the JSON data. So kind of this intermediate representation of an NS dictionary or NS array is used until the very end, and then we do the conversion. So when you call encode, sort of a summarized version of what's happening is that first a private encoder gets created. Then that private encoder is passed to the type's Encodable Protocol Encode Method. And then the encoder will get that top-level NS object from the private encoder and pass it to JSON serialization and get out the JSON data, which it returns to you. On the flip side, something that calls itself a decoder is also not necessarily something that conforms to the decoder protocol. So Json Decoder has the same sort of structure with a private type conforming to decoder, as well as a private JSON decoding storage type. And JSON decoding, which depends, whether it's an array or dictionary, depends on the JSON data that you input. So if you input a JSON array, it would be an array. Otherwise, it would be a dictionary. And this time, the container API is allowing us to read values out of this type rather than put values into it. And we're using NS for the same reasons, because that's what JSON serialization knows how to work with. So when you call decode on a JSON decoder, for example, the first thing that's going to happen is JSON serialization is going to create this NS dictionary or NS array from the data you provided. And then a private decoder, which uses that object as its sort of backing data, is going to be created. And then that private decoder will be passed to your type's initializer from the Decodable Protocol. So I want to briefly touch on some limitations of this whole system. The first one is that it's not very performant. I don't have a lot of time to tell you why that is today, but I highly recommend checking out this blog post, which is not by me, but is very good, that does some interesting benchmarking of Codable and how it compares to just using pure JSON serialization. So check that out if you are interested in performance. Another limitation is that there can be a lot of boilerplate and sort of error-prone code you have to write in some cases. Like, imagine my struct has 20 properties, and I want to encode 19 of them. The best way to do that right now is to list out the 19 properties I do want to encode in the coding keys and leave out one. And that feels like pretty tedious. Or maybe, the examples I showed you before where we wanted to just lowercase a string, we had to write out all of the rest of the method and the coding keys just to change that one property. So there's not really a good way to customize, but mostly take advantage of the compiler-generated code right now. But maybe we'll get that in the future. That said, there are some pretty awesome advantages to this whole system. As we've seen throughout the talk, conforming to Codable is pretty trivial in a lot of cases. But when we do want to do something custom, the API makes it really easy for us to do so. And secondly, as I sort of touched on before, the approach is standardized across formats you're encoding to and decoding from, which is great because you don't need to know anything about the sort of internals of someone else's encoder in order to use your encodable type with it. And same goes for decoding. So thank you so much for coming. Please come to my office hours if you want to talk more about Swift, MongoDB, encoding, decoding, all that kind of stuff. Thank you.